introductory physics to
non-introductory
physics like particle physics and general relativity. However, this time it's because over the last 4 weeks I've been teaching this enrichment course at DU to adult learners. And it was like all about Stephen Hawking and stuff, and these people really knew nothing. They were very eager to learn, but they were not the caliber of students in this class. And so I had to pitch that at a completely different level. And so now I'm coming back to you and going back to, hey, you guys know some stuff, or a lot of stuff. So hopefully I'll get the right, I'll hit my mark in terms of who I should be talking to. All right, so we are going to talk about topological field theories today, which I will admit are, even though they utilize ingredients with which I am familiar, the actual subject of topological field theories itself is well outside of my expertise. So I'm not in my comfort zone, but that's okay. If we dwelled only in our comfort zones, we would always be comfortable. So we're going to answer a few questions in the course of this discussion, hopefully. What does it mean for a theory to be topological? And we'll answer this in 2 ways. And then I'll look at a mathematical description of a topological theory. And then we'll look at a physical realization of a topological theory, described by the mathematical model that we will talk about. And we'll spend most of our time talking about the second point. Now there's a disclaimer that I have to start this with, and that is, aside from my lack of expertise, and that disclaimer is that there's going to be a point in this where I have to just pull out a big gun, and you just have to roll with it. I cannot develop it, I can't, I'll just kind of give you the result. You just have to go, okay, sounds good, and then we'll just keep going. And you'll know it when you see it. Maybe we can talk about that another time in another Physics X, but it won't happen today. So we're going to start with, what does it mean for a theory to be topological? I'm going to do my best to stay on this board so this all gets captured. You'll notice your brave leader, Matt Martin, is not here today. Thank God. Let's capture that for the record. Thank God. He is out of town, but will return next week. Now, by the way, I think next week, according to our loose schedule, we should be talking about guts, toes, and strings. Although, yeah, we'll talk about that. Guts, toes, and strings. Okay, so what does it mean for a theory to be topological? Well, let's actually take a step back and say, to specify a physical theory, we need to specify the degrees of freedom and their interactions between those degrees of freedom. And this kind of applies whether you're doing, relativistic, non-relativistic, point particles, fields, whatever. If you're in the context of field theory, then the degrees of freedom are the set of fields. And then you have interactions between those fields. And for example, in the standard model, the form of those interactions is dictated by gauge invariance or symmetry principle. You could just throw in random interactions, it doesn't matter. But these are sort of generically the things that the essential ingredients we need in a physical theory. And in defining the degrees of freedom, there is, in addition to saying what kinds of things live in your theory, there's also this idea of where things live. That is the space or the space-time upon which your degrees of freedom propagate. Because it turns out that, part of saying what are the degrees of freedom is saying, well, where can they move? Can they move in 1 dimension, 2 dimension, 3 dimensions, and so forth? So, so normally this is some specification of the space-time. In specifying the space-time, there are two roughly independent factors or attributes. The first is the notion of the geometry. So what does this word mean? So the geometry, as derived from the root geometer, we can think of as the notion of having some sort of scale in this space. And you know, we can always dig back to the very fundamental mathematical definitions of things, and we can say space-time is a collection of points, and then we're going to endow that with a notion of distance or some measure, blah, 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 blah. But I'm just going to kind of skip those rigorous details. And with the notion of scale comes the notion of distance. I'm going to write down a list of words, and then I'll come back and talk about each of them in detail. No, sorry, that's not what I meant. I'm looking at the wrong list. Distance, local. Okay. So one thing about the scale is we actually care about, you know, the distance between points, or we care about the size of things. And so what we find is if we stretch things, so if we take our space-time and we actually just grab the ends of it, stretch it, and make it bigger, if we stretch it, the geometry changes. Okay, so generally the action of stretching things changes the geometry. The notion of distance is sort of our idea in actual working with experiment and so forth, is the notion of clocks and rulers. Okay, so when I say distance, that's loosely distance in space-time. So you're talking about not just the spatial distance between me and Spencer, but also the distance in time between the event of me right now and the event of Spencer right now. Okay, those are separated in space and time. It's local in the sense that if I consider a space, then if I have the geometry in this region, say the geometry in this region is very, very flat, okay? And then I come way, way, way the hell over here and I screw it up, make it weird, that doesn't have to affect this region over here, okay? So there's this notion of locality. Things very, very far away can be messed around with, changed, and it doesn't affect locally what's going on over here, okay? And that'll make more sense when we contrast it against the next ingredient. Now all of this in mathematical manipulations is encoded in what we call the metric of the space-time. Which, just to sort of connect with ideas that we have already talked about this semester, but a lot last semester as well, and that is a 0-2 tensor, which we would generically call G mu nu, and in the special case of flat space, we call it eta mu nu. And this thing for an arbitrary geometry is itself a function of where you are, so the metric can change as you move around in the space. And essentially, if you're not familiar with what a metric is, it tells us how we actually calculate the length of vectors, okay, or the distance between points, if you think of your vector being the infinitesimal displacement vector, like so, using two coordinate differentials, and then you use the metric to contract those two, and that calculates the distance between 2 points connected by an infinitesimal coordinate shift. So I'm not going to dig really deeply into the formalism of the metric. That's something which, if you really care about, you should take DRM and learn it. But it pops up in a lot of places. Okay, and by the way, when you do utilize a metric, you have in mind that you're throwing down some coordinates on the space, because you can't really write a metric without specifying some coordinates to express that metric in terms of. Okay, so there's the notion of the geometry, and then there's somewhat separately the notion of the topology. Okay? And there's sort of some analogous words for topology, so it doesn't care about scale, or one might say it's scale invariant. So an interesting thing about this is that stretching, but not tearing, doesn't change the topology. Okay. So the famous example, which you've all seen a gazillion times, is that I can take a donut, and by continuously deforming it, without tearing it, I can manipulate it into a coffee cup. All right? And so one would argue that the donut and the coffee cup have the same topology. Really interesting. I mean, really, it's like you could teach a kid topology with some Play-Doh. Like, here's the Play-Doh, make a donut. Now take your donut and turn it into a coffee cup, but you're not allowed to tear the Play-Doh. If you tear the Play-Doh, such a weird word. If you tear it, you've actually changed the topology, because what you've done is you've introduced a boundary. And then, you know, if you start allowing yourself to tear it, you can do all kinds of crazy things. Like you can take this guy and you can tear it, and then you can tear it some more, and you could eventually join it into something like this, which has definitely got a different topology than that. So once you open up the floodgates to tearing things, generally speaking, you can change the topology almost arbitrarily. So yeah.
So when you say coffee cup, is the top and the bottom of the coffee cup like continuous boundaries?
You have a coffee cup in front of you, Spencer.
I know.
That can be continuously deformed. So I should say we're technically speaking about the surface of the coffee cup. The volume is not part of the space. Just like with the donut, we're only talking about the surface of the donut, not the interior.
I'm talking about like the top and the bottom, right? Is that like a boundary now because it's like a right angle, or is it?
No, it's smooth. It's smooth. Yeah. I see what you're saying. So like it's an edge constituted boundary. So there's more precarious things that we can say about it. Like you have to have a smooth. Well, you don't necessarily have to have a smooth space when you're doing topology, but if you're also going to endow it with some geometry, then typically to do, say, relativistic physics or something like that, you need to also incorporate smoothness, and that's where you would not allow your space to have edges. Okay, that's not saying you can't do physics on things with edges. It's just it requires more tools than what we've got with sort of our standard description of gravity or of geometry in terms of gravity through Einstein's general relativity. Okay, so we've got that. It's topological. It's global as opposed to local for the following reason. If I have a space and I'm sitting over here looking at this little region, okay? If I come in way over here and I actually change the topology by adding in a handle, I've changed the topology of the space, period. The topology cares about the entire space all at once. So there is no notion of, I only care about my little patch of what's going on right over here when it comes to topological questions. They care about the entirety of the space all at once. And lastly, to describe the topology of a space, you usually have to use something which is sensitive to the topology but insensitive to the geometry, because if you're trying to describe it with something that cares about the geometry, then that's not really going to do you very much good, because these have different geometries but they have the same topology. So if your descriptor of the topology changed with the geometry, it would say these are different, but they're clearly topologically the same. So you have these things called characteristic classes. Of which there are many, and they're defined in different ways. And these characteristic classes essentially are features of sets of spaces which are invariant under continuous deformation. So the donut and the coffee cup would have the same values of the various characteristic classes because they are topologically equivalent. And we won't need to go into, say again?
Oh, can you say that again?
So for example, one characteristic class is the first cohomology, the first de Rham cohomology. That's one we actually talked about last semester when we talked about using differential forms to do topology. And so these would have the same value of the dimension of their first cohomology. Because the dimension of the first cohomology only depends on the topology of the space. And since these have the same topology, they have to have the same dimension of the first cohomology and dimension of the second cohomology and the Keith-Betty number, blah, 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 blah. Okay, so, all right. Yes. Okay, so now, what's important is that, and I think this is a facet which is often, well, first of all, let me say, these two things are not 100% disjoint from each other. So I can't take a space and give it any metric I want without knowing something about the geometry. And what I mean by that is giving the space a metric everywhere throughout the space. I can always, for a region of the space, make the metric look any way that I want. I can, in a local region, change my coordinates, define things so that this metric, I can actually make the metric look flat, as long as we're on a manifold. However, to put a metric on the entire space usually requires that I know about the topology of the space. Okay? And the reason why that is important is, for example, or a reason why that's somewhat obvious is here are two-dimensional spaces. I'm going to draw it, and then I'm going to convince you that the drawing is inaccurate. Okay, there's a surface of a sphere, and there's the surface of a torus. This is, if you define it the right way, this is flat, and this is not flat. So if I put a metric on this, I can put a flat metric on it, but I can't put a flat metric on this because this is intrinsically curved. But the reason this is intrinsically curved has to do with the fact that it's a sphere and not a donut. So all I'm trying to get across to you is that I say these two things are somewhat separately specifiable, but not entirely separate. There are some things that link them. Okay, so now the other thing that I think really goes kind of under the radar is that normally when we do physics, even the physics you were doing from physics 100, you actually cared about both the geometry and the topology of the space. I mean, physics cares about everything that's going on. The two issues with that are, one, usually the topology of the space you were working on was trivial. That is, the space was infinite. And so topologically, nothing interesting was happening. Usually, to get some interesting topological effects, the space has to be compact in at least some direction. So, for example, an infinite cylinder is topologically interesting because it's got that one compact cycle. And so we get some interesting effects that arise from that non-trivial topology. Even if you do physics on topologically non-trivial spaces, you still care about geometry, okay? But you certainly get effects that arise because of the non-trivial topology. So, a simple example is when you do quantum mechanics. Many of you have seen quantum mechanics. That's more than I could have said for the last 4 weeks. Many of you have seen quantum mechanics, and you know that there's a big difference between doing quantum mechanics on an infinite cylinder and doing quantum mechanics in an infinite two-dimensional plane. Because for one, the momentum along the S1 here is quantized, whereas here it's not. Okay. So there's lots of things that crop up when you start looking at topologically non-trivial directions or parts of your space. But what we are interested, so the meat of that statement is topology and the effects of topology are everywhere in physics. There's the potential of saying, hey, wait, this is happening because the topology is non-trivial. What we want to talk about today, though, is how do you narrow in on just this part of it in such a way that you can completely ignore the geometry? Because the truth is the theories are complicated in part because these two things are playing with each other, influencing each other. And we'd really like to just completely get rid of this and just have this part left over. And this is the subject of topological field theories. Okay, and that's what we're going to see in at least one example of today. Okay? So in defining topological field theories, it turns out there are two categories of topological field theories. The first are what are called Schwarz-type topological field theories. And these are probably the most obvious. Okay? So one could say geometry is encoded in the metric g mu nu. So if you want a theory that doesn't depend on geometry in any way, shape, or form, what do you want that theory not to depend on? G mu nu. Okay? So in a Schwarz-type theory, S, which is the action of the theory, one way to define it, S is independent of g mu nu. Okay, so if I can write down a Lagrangian, integrate it over a volume, or integrate it over the space-time, and that thing, which is we call the action S, if it doesn't depend on the metric at all, then that theory is manifestly topological. Okay?
So the Lagrangian could have g mu nu in it, it just has to be integrated over the whole space. Like you have to trace over or integrate over g mu nu. It can still be in your dynamics somehow.
No, not for a Schwarz type.
Okay.
It can't appear at all.
Okay, at all, like in the Lagrangian density, for example.
Right, and I'll come to that point in a few minutes.
Right.
So, because I mean, you know about this, and most people don't. But when you define the integration measure over the space-time, then you've got this square root det g function.
Right.
Yeah, well, I'll talk about that in a few minutes. But that's included in this statement. Like it can't even appear there. Okay, the second type, which is more complicated because Witten came up with it, is called a Witten type. And I'm not going to talk about examples of this because they're much more complicated, but generally speaking, you start with a Witten type situation, you start with an S that uses a metric g mu nu. So you write down a starting point. Oh, by the way, I should say that if you give me an action S, which is independent of the metric, then you can do classical physics with that through the Euler-Lagrange equations that you would derive from S. So these are the equations of motion, they're Newton's laws, and so forth and so on. So you can do classical physics with this S through the Euler-Lagrange equations, or you can do quantum physics through the path integral, which uses e to the I over h bar times S as the weight in a sum over paths, which is part of the calculation of probabilities in a quantum mechanical theory. So you can have, classical topological field theories and quantum topological field theories, although it's usually in the quantum context where these are actually interesting. In a Witten type theory, what we find, and this is specifically for quantum mechanical cases, is you can start with an action which uses a metric g mu nu and has a nilpotent symmetry. So So that is, there's some transformation delta that you do to the action, and the action is invariant. That's what it means to be a symmetry. It's nilpotent because if you do the transformation twice on anything, you get 0. And you might remember we've seen an example of nilpotent. A nilpotent operator is the exterior derivative on forms. You do that twice, you automatically get 0. And what you can find is that in this context, with some other conditions, you discover that a class of operators, it turns out these would be closed operators, a class of operators have correlation functions which are independent of the metric. So the reason this is important is because you have to remember in a physical quantum mechanical theory, you don't go out and measure S. Like S is not something you see and touch and do experiments on. You see and touch and you actually experiment with correlation functions. Those are the things you measure. And so what Witten discovered was that in a certain context, you can find that the actual physical content of these quantum mechanical theories, at least a closed subset of the physical content, is independent of the metric. You can change the metric all you want, and this part of the theory doesn't change. And so that part of the theory is then topological. And it's a closed subset, which is important because that means you can consistently ignore everything else and just focus on that subset of the theory. So those are Witten-type topological theories. We're not going to mess with this. We're just going to look at a more simple example of a Schwartz type. And so the question we turn to now is, what does a topological field theory look like? And I've sort of secretly stuck in the word field theory because in almost all contexts that I know of, when you're doing topological theories, they are field theories of some type. So let's start with something with which we're all roughly familiar at various levels, and that is consider electromagnetism in the context where you're used to it, and that is four-dimensional flat space-time, so Minkowski space. 3 spatial dimensions, 1 time. And the action for that theory, without any source terms, is given by an expression like that, where this guy right here, F mu nu, is the derivative of the vector potential A nu, anti-symmetrized over those indices. Here, A mu is just a combination of the scalar electric potential and the magnetic vector potential to form a 4-component vector, as you need for a relativistic theory. And then the content of F mu nu, to really bring this down to Earth, is just the components of the electric and magnetic fields in a particular combination. And then minus everything that don't off diagonal. So this is really just an action written in terms of the electric and magnetic fields. It's just written in a very highfalutin way because it makes the relativistic invariance manifest. Okay. So if we consider that, you'll notice that in that expression, there's no G mu nu. Spencer.
So Technically, every time you have index notation, you can introduce G mu nu and raise it and lower it.
Sure.
So to say that it's invariant of G mu nu is to say that you're contracting both the mu and the nu, right? Or you have like a set.
Well, look, I mean, I can always say G mu nu, G nu alpha, which is delta mu alpha. This is secretly 1. So I could always take a 1 anywhere I want and blow it up into a metric and an inverse metric and then go, oh, it depends on the metric. But it doesn't really, because this combination is just 1.
Well, for the.
Yes, Spencer, your concern is legit. Gosh, you guys are so smart. No, this is incorrect. Okay, this actually does depend on the metric for the reasons which Spencer is getting at and more, okay? Remember, I was going to see if I could actually convince you all that this was topological and then be done. And then you'd come back next week and go, but I looked it up on Wikipedia and it said it was no. Yeah. Okay. No, remember, the thing I defined for you is this. I didn't define this. And that's where we have a problem. Because to get this thing from the ingredients of the theory, we actually have to use not 1 metric, but 2. And I should say, since we're in M4, G mu nu is the metric of Minkowski space, so I'll write it like that. So this is mu alpha nu lambda, and I just want to make sure I'm using the right mu lambda beta. So we can just copy. So f with 2 upper indices is built from f with 2 lower indices using 2 factors of actually the inverse metric, but still, you know, you've got a metric that's coming into the story. So there really is a metric hiding in here, but it's worse than that because it turns out that the integration measure itself comes with a factor which is sort of invisible, and that is it comes with a factor of the square root of minus the determinant of eta mu nu. Okay? Now why didn't I write that minus the determinant of eta mu nu?
It's 1.
Because it's 1. Okay, eta mu nu, if you write it as a matrix in Cartesian coordinates, looks like that. So the determinant of that is minus 1. The minus makes that a 1, the square root is 1. You're done. Okay? But we would have to remember this factor because if we went to, say, curved space or flat space with curvilinear coordinates, like spherical polar coordinates, then eta mu nu would go to some more general metric, and then our integration measure would become this. Okay? Which is, which in a more general case, this is certainly not 1. Okay, so it's sitting there. Now you might say, well, why this? So why do we need that factor? What does that do for us? Well, we talked about this a little bit last time, so why this, and I'm gonna go ahead and use a bit of notation. I'm going to define the determinant of G mu nu to be just G. Okay? So the question is, why do we have this factor of square root of minus the determinant of the metric? Why do we have that there? Well, very quickly, when we were talking about forms, we said that if you have the volume element d4x, where this is defined using some coordinate system x mu, and then you want to ask what does that look like in a new coordinate system, say dx4 prime, then we have a factor of the Jacobian that comes in when you transform these coordinates, and the Jacobian is of course the determinant of the matrix of partial derivatives defined by your coordinate transformation. Okay, so this is something you should have seen in calculus. And so we can of course rewrite this and say dx4 prime is d4x over the Jacobian. Okay. Now that immediately tells us that if I tried to do an integration and I just wrote this, that's not coordinate invariant, right? Because if I do a change of coordinates, it transforms into something like that, which is not what I started with. A coordinate invariant is something which, at the end of it all, looks like what you started with. Okay? But if we instead consider not d4x, but d4x square root minus g, then we've got a special thing that happens, because if we transform coordinates, the metric itself transforms by a set of partial derivatives. Okay? And because I'm taking the determinant of this, right, then what we find is that when I transform the metric determinant, I end up picking up a factor of the square of the Jacobian. Okay. So at the end of the day, this particular combination is invariant because d4x transforms with a factor of 1 over the Jacobian. The square root of the determinant of the metric transforms with a factor of the square root of j squared. So the j and the inverse j cancel each other. And so after a coordinate transformation, this actually ends up looking exactly like what I started with. Okay. So the square root of the determinant of the metric is not something which we looked at in general relativity because we didn't do action principles so much. We just looked at Lagrangians, or actually just equations of motion. But when you're looking at action principles where you're actually doing an integral over space-time, it's an important factor. And for this story, it's important because it's one more place where the metric comes in. So the metric is hiding in two places here. It's hiding in the fact that these indices are raised, and it's hiding in our integration measure. Okay. So if I were to write out what this thing is in truth, it would be minus 1/4 the integral of d4x root minus g mu lambda g nu beta f lambda beta f mu nu. And now no one would argue the metric does appear there. Okay? So that's definitely not topological. However, oh my God, every single time. However, in trying to get something that would work, we might recall a statement that I made when we were talking about differential forms last time. Which wasn't really, it was a long time ago. But.
Recall from lecture last month.
You know, you're supposed to crystallize all this. I gave you time to think about it, internalize it.
I'm not complaining.
Yeah.
Crystallizing.
I hear you complaining.
It's all
Okay. So there was a statement that I made sort of towards the end of our differential forms lecture where we were talking about integrating differential forms. And I said, if you integrate a P form over a P-dimensional space, then this entire thing is coordinate invariant. And we actually dug into the details of why that is, where this is a P-dimensional oriented space, or oriented manifold, actually. So one of the reasons why this happens is that if I blow up the expression for a P form, remember this is 1 over P factorial times a set of components times a set of anti-commuting coordinate differentials. And it was really this set of anti-commuting coordinate differentials which was the thing that really had the magic that made this a coordinate invariant integration measure. So if you want to go back and sort of review how that worked, just go back to the video or the notes of the differential forms lecture. But it really, I actually wrote it down because, and pointed out that the Jacobian that you normally would expect for the transformation is actually taken care of by the anti-commuting nature of these things. So, so what this means is that if we take p equals to 4, that is, if we take a 4 form and we integrate it over space-time, okay, then this is a coordinate invariant thing. So we could take the electromagnetic action and add to it the integral of some 4 form. Okay. And we know that this one's coordinate invariant because we've done all of our careful index notation, using metric factors, et cetera, et cetera. And then this is invariant because of the nature of forms. Okay. So one might ask, well, what would this look like? So what 4 form might we put in there? So we have to go back and remember the ingredients that we started with, because at this point I don't want to add new ingredients to the story. I want to work with the ingredients that we've already got. So the ingredients that we already have are that we have a 1 form. Okay, the electromagnetic vector potential A mu is really the components of a 1 form. And then we actually have a 2 form. Okay. Neither of those are a 4 form. So, in the absence of a 4 form, what can we do?
Wedge product.
Yes, we talked about how to multiply forms. And in particular, we learned how to multiply forms so that the result is itself a form, and that requires us to take the wedge product. So without any further ado, the first guess at what this might be is to take F2 wedge F2. That is, take the wedge product of F with itself, because that's clearly a 4 form. And so let's look a little bit at what that would look like. So F2 wedge F2, if we remember the definition of the wedge product, we have for the components 2 plus 2 factorial, 1 for each of these 2's, over 2 factorial, 2 factorial, and then each of these is described by a 2-index object. Okay, and oh yeah, something I was going to say up here. So these, yes. So for the anti-commuting coordinate differentials, we're going to use a shorthand, which is that we have this guy where it's understood that because they anti-commute, that is true. Okay. So the way that we're going to notate that is we're just going to call this quantity epsilon mu nu d2x, where epsilon mu nu is just the Levi-Civita with 2 indices. And you can generalize that to the Levi-Civita with any number of indices. Okay. So this is just a nice way of encoding the fact that these coordinate differentials should anti-commute. And so here we have 2 anti-commuting differentials for each of these factors of f. And so we're going to get an epsilon lambda rho d2x, and then an epsilon mu nu d2x. Okay? And now there's a lot of stuff that happens which I am not going to go through. This is not the big thing, though. This is a minor thing, which you can just do because it's details. So first of all, this is going to give me a factor of 6. This means I anti-symmetrize over all 4 of these indices. Okay, we're in 4 dimensions, so mu, nu, rho, and lambda take values 0, 1, 2, 3. Remember, 0 is what we call the time direction, so there are 4 space-time directions. Each of these has 4 values. There are 4 of them. We want to completely anti-symmetrize over the exchange of any 2 of them. And so if you actually sit down and think about it long enough, you realize there are 24 of those. So this thing will end up being this, plus 23 permutations, with minus signs on half of them. Okay, so that the net effect is that it's completely anti-symmetric under the exchange of 2 indices. And then, of course, these 2 things. And then the step, which I'm definitely not going to show, is that this can be reduced to the following expression. And this is really, really hard to tease out of the literature, because there's kind of a step there that wasn't obvious. So first of all of this is being condensed into this product, but this product is still defined where this is an anti-symmetric combination of these 2. Okay, so what I have in mind here is that this thing is itself d lambda rho, or d lambda a rho minus d rho a lambda. And then this one is anti-symmetric over those 2 indices. What I mean is, in this expression right here, I would not swap rho and nu. Okay? However, up here in anti-symmetrizing here, I do allow swaps of all indices with each other. Similarly, you've got to be careful because this thing right here is not the same thing as this, for the same reason. Okay? So if you actually want to write out all of these permutations, you want to write out all of these Levi-Civitas, and then you want to condense it back to this, you just have to keep that in mind, that the expression you're ultimately writing is in terms of ingredients which are a little bit different than what you started with, and you just have to remember the implied anti-symmetry of the indices in these F mu nus. Okay, so I don't want to get too hung up on that, because the bottom line of it is that, where is it? Yeah, so the bottom line of it is that this term, F mu nu wedge F mu nu, really boils down to something like the following. d4x epsilon lambda rho mu nu times F lambda rho F mu nu. Okay? So our theory can start with the electromagnetic action plus this term. And the important observation now is that this term legitimately does not depend on the metric. In a sense, what we've done is we've used the Levi-Civita symbol to contract the indices, where before we used the metric or the inverse metric to contract them. So the idea is essentially this. In a geometry, there are 2 tensors that you have at your disposal. You have the metric of the geometry and the inverse metric. But you also have the Levi-Civita with any number of indices. Those are both well defined on a geometry, an orientable geometry. If you use the metric to do anything, then you're using the geometry itself, the notion of distance, because that's tied to the metric. But if you can do all of your index combinations and so forth just using the Levi-Civita, you're not using the metric. Okay? So what we find is that this term is topological. It's really topological. And you'll notice the distinct absence of that square root of minus the determinant of the metric.
I think that's good stuff.
Say it again?
That was a bad joke.
That was a good joke.
Don't make bad jokes. No bad jokes allowed. No bad jokes for you. Okay. So, so let's actually write down what this thing looks like. I'm gonna erase and then rewrite, erase and rewrite. So we've got minus 1 over 4, the integral of d4x square root of minus g rho g lambda mu g rho nu f lambda rho f mu nu. So that's our electromagnetic term. And then we've got our awesome new and great topological term, which we will just lead off with k over 4 just to give it some leading coefficient, which could be different than the coefficient in front of the electromagnetic term. And then we have d4x epsilon mu or epsilon rho lambda mu nu f rho lambda f mu nu. Okay. This theory is not topological in that sense that I mentioned earlier. In the sense that, yay, there's a topological term, but there's still this term which has the metric in it. And what's important is that the stuff in this term, or the stuff in this term I should say, appears in this term. So the A mu, the vector potential that this is built out of, also appears here. So you can't like squint your eyes and just look at this term and say, I've got a topological theory. No, because if A mu is doing something interesting over here, it's doing something interesting over here, but what it does over here depends on the metric. But this is how physics is in general. Physics in general does care about the topology, but it also cares about the geometry. So this is what most physical theories look like. What we would like to do is somehow argue that this thing can, for some situation, be reduced to only this term. Somehow find some magic that makes this go away. And now for the big gun. So the big gun is that it's labeled big step in my notes. The big gun is that when we do quantum field theory, this is after all a field theory, when we quantize this, what we discover is that various quantities, various parameters, which we normally think of as constant, so for example, masses, couplings, etc., actually change with the energy scale. And this is a process called renormalization. Yeah, we're not going to do renormalization today, but generally speaking, what you discover is that when you do an experiment and everything that you're putting into the experiment is at a certain energy, so you're bombarding something with photons that have a certain wavelength, then to describe the quantum mechanical reaction of your specimen, you have to use the masses and the charges and so forth appropriate to the energy of the photons you're shooting in. And if you do the same experiment with higher energy photons, then it turns out that to describe things, the masses and charges and so forth that you use should have different values. So the masses and charges and so forth, they are functions of the energy that you're doing the experiment with. So that might lead you to the obvious question, well, when I look up in the back of the book the mass of the electron and the charge of the electron, what does that mean? And no one tells you this in the backs of the books, but those are measured at zero energy. Those are effectively very long distance, very low energy experiments, and that's where you're stating the mass of the electron or the charge of the electron. If you go to higher energies, those effective values are going to change significantly in many cases. Now, one of the important ideas in that is that any coefficients in front of terms in an action or a Lagrangian are basically couplings. And so these coefficients could ostensibly change due to quantum mechanics. And so we might ask, is there an energy scale where one of these coefficients blows up, or at least is very, very much bigger than the other, so that we can effectively ignore one term over the other. Okay? Part two of the really big step, because we're not going to do quantum mechanical renormalization, is that a rule of thumb is to figure out how things scale with energy. We start by calculating what's called the length dimension of various terms in the action. So to give you an idea of how this works, whenever I encounter a derivative, so remember our theory is built out of A mu and D mu, basically derivatives and factors of A. Derivatives, which are secretly this, scale as 1 over length, and the gauge fields themselves also scale as 1 over length. And one way that you can think about that is when you do a gauge theory, to form the covariant derivative, you actually pair the ordinary partial derivative with a correction from the gauge field. So those two things have to scale the same, otherwise you wouldn't have the business subtracting them. So what you can do is you can take your various terms in the action and you can figure out their overall length scaling. And then the rule of thumb that emerges from looking at lots of cases of quantum mechanical renormalization is that low energy physics is dominated by largest length dimension. Okay. So let's actually do this for our theory and see what happens. Okay. And this is not in any way, shape, or form obvious, but it is something we have to, it's a step we have to just accept in order to move on. So good. What did you do when this was held from 11:30 to 12:30?
I have a lunch thing today that's special for this week.
Oh, well, aren't you special?
Well, I'm not.
Okay, yeah. That's fine. So if we very quickly survey these terms, notice we've got an F mu nu here, we've got F's here. So essentially, this is going to have 1 over length to the 4. This is going to have 1 over length to the 4. Which means that these two terms in the action are basically going to scale the same as we adjust the energy scale of the theory. Which means that in this case, we don't really have a way to make this term dominate. However, and this is where the magic happens, in 2 plus 1 dimensions, a very critical thing changes. In 2 plus 1 dimensions, our electromagnetic action looks the same. Okay? The only thing that's changed is we're integrating over d3x. The metric is a 3 by 3 symmetric matrix. Everything depends on 3 coordinates. The F's and the A's they're built from, the F's are 3 by 3 antisymmetric matrices. The A's, the vector potentials, are 3 component things. Okay? But otherwise, the form of this looks just like this. However, here we have a problem. Because in this case, we can't do this. Okay? Because remember, we built this by saying we're going to integrate a 4 form over 4 dimensions. But now we're only integrating over 3 dimensions. We have to integrate a 3 form at most. So the question is what 3 form are we going to use? Well, the simplest answer is let's just take a wedge product of the vector potential and the 2 form. That's a 3 form. And so what we find is that in 2 plus 1 dimensions, there it is, yes. In 2 plus 1 dimensions, our new topological term going to look like that. Again, the key thing that changed is you can only integrate forms of the degree of the dimensions of your space-time. And so when you change the dimensions of space-time, it changes what forms you're allowed to work with. It doesn't change anything in this story. Okay? But now you can immediately see, if we do the length dimension counting, in this case it's the same. But here now, we have 1 over L cubed. Okay? Well, 1 over L cubed is bigger than 1 over L to the 4th. And so what we discover is that at low energies, and you can go to low enough energies, this term dominates. So at low energies, you can actually ignore the usual electromagnetic interactions in a system described by this entire action and just focus on this term. And again, this is important because you're not just arbitrarily squinting your eyes and paying attention to this one and ignoring this one. You're literally saying that at low energies, these excitations do not contribute in any manageable or in any measurable way to the dynamics of that's described by this action. Okay? So this is a topological theory. This is a topological field theory. And at low energies, it's described by this term in the action, which is also called a Chern-Simons term. So our final question is, okay, you've given me all that abstract math land bullcrap. How does this happen? How does it actually happen? Can you actually get a system where you have a Lagrangian or an action like this, and then you have this nice limit you can take where the dominant term is the Chern-Simons or the topological term? And the answer is yes, you can do it. And it turns out not only can you do it, but it's cool that you can do it when you can do it, because it's the only time that you can actually get something interesting. So without any further ado, and this is not going to take long at all, and there's just a wealth of stuff that crops up in this story. Consider confining electrons to a 2D surface that is a 2 plus 1D space-time. So, graphene if you like. Pick any two-dimensional surface you want. There's numerous experimental methods for confining electrons to a two-dimensional surface effectively. And turn on a strong perpendicular B field, magnetic field. Okay. Clearly this is electromagnetism. We're talking about electrons, we're talking about B fields. Everything is in terms of the vector potential A, the FB news, and so forth and so on. It's a 2 plus 1 dimensional theory, okay? Because we have effectively confined things so they can't move in that third dimension, that third spatial dimension. And it turns out that the physics, the low energy effective field theory describing this is exactly described by the electromagnetic action plus the Chern-Simons action. This guy right here. Okay. So if you do this, if you confine things to a two-dimensional, electrons to a two-dimensional surface, turn on a strong B field, and then only probe it at low energies, okay, don't do anything at high energies, then, as we argued, this term goes to 0, and you have a purely topological theory governed by this Chern-Simons term. Now you might say, okay, what do I do with that topological theory? I have a theory, what can I do with it? What can I compute? So one of the interesting things about this theory is that its stress energy tensor, which is generically defined, there's some proportionality constants, but the stress energy tensor is basically defined as the variation of the action with respect to the metric. This is a definition which you might or might not have seen, but this is the common definition in at least curved spacetimes and so forth. So if I have an action, I can vary the action with respect to the metric of the space-time, and that's the definition of the energy momentum tensor associated with that geometry. But if we're in this low energy limit where the only term is topological, what is this? It's 0. In the topological limit, this doesn't depend on the metric. So varying the action with respect to the metric is 0. That means the energy momentum tensor is 0. But if the energy momentum tensor is 0, that means the Hamiltonian is 0. There's no local notion of energy and momentum. So when you want to do a calculation, you might say, okay, I want to solve the Schrodinger equation with h equals 0. You guys want to do that? Might take a while. What are the energy levels associated with the Schrodinger equation?
0.
They're 0. The left-hand side is 0, the right-hand side needs to be 0. Okay? That is trivial. That's not interesting. But that's only half of the story of the quantum mechanics, right? Because not only do you want to solve for the energy eigenvalues, but you also want to solve for what? The eigenvectors, the wave functions. Moreover, it's not so much that we care about the actual form of the wave functions, more so than we would like to know how many solutions are there. And so finding the number of solutions in this problem is what we call determining the degeneracy of the ground state.
With h equals 0 isn't it an infinite number of solutions?
No. You have to be a little bit, well, okay, so you're used to solving this in terms of local physics. However, in this case, this So you're used to solving for the wave function in situations where, well, actually, I don't know when you're used to solve for the wave function. I mean, when you solve for the wave function, you have not just the equation itself, but you also have various boundary conditions that are applied, right? The boundary conditions are usually subsumed in the definition of H, right? You say, I've got a particle in a box, so I've got these boundary conditions here and here, but that's actually encoded into the form of H because you give it this infinite, well on each side. However, what we have to remember here is that space-time itself comes equipped with boundary conditions. Because especially if this is topologically non-trivial, the space-time itself could have holes in it, and so there could be periodicity as you move around certain closed cycles on that space. So solving for the solutions of psi, where you're incorporating these various boundary conditions, is non-trivial, and there's not an infinite number of solutions, okay? Because the psi's have to not only satisfy this Schrodinger equation, but they also have to satisfy the boundary conditions. But the point of this is that the psi's that solve this are determined purely by the topology of the space.
So your number of solutions would just be your number of boundary conditions.
Well, it's not the number of boundary conditions itself directly, okay, but it's tied to that. Okay, so at the end of the day, the number of solutions or the degeneracy of the ground state of this particular topological field theory is directly tied to topological invariance of the space on which this is defined. Because after all, it's topological. If this was the shape of the space and then I stretched it, I'm not technically changing the boundary conditions. I'm still saying it's periodic here, it's periodic here, it's periodic here. So the number of solutions, the degeneracy of the ground state can't change. So if you forgot about that there was some weird complicated geometry and I just handed you a quantum theory with some, albeit I have to specify the boundary conditions, if you solved for the degeneracy of the ground state of that quantum theory, you would equivalently be solving for the topology of the underlying space. So this is what people mean when they say that a topological quantum field theory computes topological invariance of the space on which it lives. And remember, it can do that computation because the computation you're doing is not screwed up. It's not tainted by effects that come from the electromagnetic part of the theory because you've gone to the low energy limit and this term is not really contributing to what's going on. Now you might say that's a bummer because it only works in 1 plus 2 dimensions, but that's actually the great thing. Because if I said create a topologically non-trivial 3 plus 1 dimensional space, that's really hard to do because we live in 3 plus 1 dimensions. It's hard to take this space-time we live in and bend it at our will. However, it's very easy to do that with 2 plus 1 dimensional spaces. You know, because remember, 2 plus 1 means a 2-dimensional space plus time. So I can take this thing and I can make it topologically non-trivial. So the fact that this is actually a useful tool in 2 plus 1 dimensions pairs nicely with the fact that in 2 plus 1 dimensions, that's the context where we can actually, in a lab, create non-trivial topologies and then test out these theories. Okay. All right, that's all I got for today. I'll put that away right over there. And by the way, this is literally just cracking the surface of a very big subject. And these Chern-Simons theories, particularly in 2 plus 1 dimensions, are super cool. If any of you have heard of anyons, things with arbitrary statistics, then these actually crop up in this context of 2-dimensional trapped electrons in strong magnetic fields. So there's a wealth of interesting physics that comes into this. Lots of condensed matter people work in this area. I am not an expert, but if any of you want to go and develop expertise in it, I'd be glad to have you back for a guest Physics X lecture. Otherwise, we'll see you next week for Guts, Codes, and String.